Okay, let's get started. Thank you everybody for coming. Today, our seminar is going to be delivered by Giovanni Tomaselli, who is a new member here. He arrived here about a month ago, having done his PhD at the University of Amsterdam with Daniel Baumann and Franco Bertoni. That was following his undergraduate work in Pisa. And Jimmy is interested in both astrophysics and particle physics, and in particular, he's interested in how one can further our understanding of fundamental physics beyond the standard model using exotic astrophysical phenomena. And his remit today is to entertain us with a story about gravitational atoms and black hole binaries. So Jimmy, take it away.
Okay, thank you, Chris. Okay, let's get started. Okay, so today's talk will be a review of a series of papers. All of them completed either by Hong Sheng, who was also here until very recently, or myself. But they were done while we were at the University of Amsterdam. So these are all papers by many people in Amsterdam. The series of papers can now actually be considered complete in some sense, because many of the topics discussed in these papers are interconnected and needed to have some conclusion to be fully self-consistent, which we finally achieved a few months ago. So I'm not very happy I can tell the full story. This also means I don't have enough time to tell all the details, but I'll tell you the most important parts of the story. But I will still give some more emphasis to the last two works of the series, which can be seen as the conclusions. Okay, so as Chris said, the main motivation behind this work is to do fundamental physics. So in a simple words, finding new particles. Okay. Now, historically, the method that has been most successful for this purpose has been going to higher and higher energies in particle colliders. Increase the energy, at some point you reach the mass of a new particle and you find it. Now, this strategy works very well if the new particles are coupled strongly enough to the ones we already know. So the standard model. This wouldn't work with particles, hyperradical particles, that only couple very weakly, for example, only gravitationally to the standard model. So it's possible that new physics actually hides not at higher energies, but at weak coupling instead. Now, as I'll explain in a minute, there are many proposals for this kind of new physics beyond the standard model. And as I'll explain in this talk, we can use black holes and gravitational waves to probe this kind of new physics. Okay, so what are these new particles that I have in mind? Mostly ultralight bosons, and I'll focus on scalars in this talk. One very famous example is the QCD axion that is introduced to solve the strong CP problem. That's the problem of why even though CP is not a symmetry of the standard model, it is a symmetry of the strong interactions. Okay, and a new ultralight pseudoscalar can restore this symmetry, and is considered it's probably one most popular solution to address the problem. There are also phenomenological models of ultralight particles, such as the famous fuzzy dark matter paradigm. Now, to be honest, the original proposal of fuzzy dark matter is now excluded by observations. So the window around 10 to the minus 22 electron volts is not compatible with constraints from Lyman alpha forest and ultra-faint Wood galaxies. But different mass windows still work. And there are good phenomenological reasons to study this paradigm. And more generically, ultralight bosons are expected from string theory, in the sense that from string compactifications, one generically gets many Kaluza-Klein zero modes that then receive a small non-perturbative corrections and get a very small mass. Okay, this is called the string axiverse scenario, where one expects not just one axion, but many axions, potentially with many different masses and different couplings to the standard model particles. And there are also other scenarios, such as the real axion, where the axions or axion-like particles are used to solve the hierarchy problem, that is, relax the electroweak scale to energies much below the Planck scale. Now, in most of these cases, except the second one, there is no abundance in the universe. So these particles are not necessarily produced by some cosmological mechanism. So how do we probe them? How do we probe something that is there in nature, but just not in large numbers? So the key mechanism that allows us to do this is called black hole superradiance. So now let's take a step back and explain what is that and how does that work.
So to explain dark matter, you would need it to be abundant, right? If the axions make up the dark matter, then
exactly. As I said, in the second case, this observation does not apply, but still, superradiance can still happen even if you have some non-zero abundance. But even if you don't, then superradiance is gives you a way to probe fields that are not abundant in the universe. Okay, so what is superradiant? Let's take a step back and look at spinning black holes. Okay. Now, spinning black holes don't just have an event horizon, which I have depicted here in black, but also another region around it called the ergo region or ergosphere, which has this weird shape in the extremal limit. Now, one possible definition of the ergosphere is the region where the J00 component of the metric is negative. Okay, this means that the Killing vector associated to time translations of the metric becomes from time-like to space-like inside the ergosphere. And now, as a consequence of this, the energy of a particle, which is the conserved quantity associated to time translations, is allowed to be negative inside the ergosphere. Okay? Now, if you throw a particle from outside, because the energy is conserved along the geodesic, it will be positive inside the ergosphere as well. So to have something with negative energy, you must create the particle inside the ergosphere somehow. Okay? And so that's what Penrose realized in the 70s, maybe late 60s, when he introduced the Penrose process. So he proposed this Gedanken experiment where we indeed throw a particle with energy E and let it, for example, decay in two particles inside the ergosphere, one with negative energy and one with positive energy. Now, because the one with negative energy is not allowed to exist outside the ergosphere, it's trapped inside. We may imagine that it at some point is absorbed by the black hole. The other one instead can escape. Now, by local conservation of energy and momentum, if this one has negative energy, the one that escapes must have more energy than the one that we threw in initially. So in fact, the black hole has absorbed some negative energy and also negative angular momentum. And we have stolen some energy from it. Okay, this is called the Penrose process. If you do the same thing with a wave packet, people call it superradiant scattering. Okay. Now,
but this can work for any kind of particle, be it fermion or boson.
Good question. Not for fermions, only for bosons. The reason is that if you repeat the calculation with particles, you realize that what increases the energy is not an increase in the energy of a given particle, but you increase the occupancy number of a given state. And this is forbidden by Pauli's exclusion principle. So you can do this with bosons, but not fermions. Okay, the frequency of the wave stays the same after the scattering. Okay. Okay, now if you just throw a wave towards a black hole and it comes out amplified, that's funny, but probably not very interesting because then the wave goes away, okay, and doesn't come back. But if the particle has a non-zero mass, such as on all the proposals for the understanding of the physics I mentioned earlier, then it can just come back towards the black hole because maybe it's in a bound orbit, okay? And this initiates an instability because it's a positive feedback process. it scatters, it gets some energy, and it comes back, it scatters again and again and again, increasing, like getting out of the black hole more and more energy exponentially. This is called the superradiant instability. And can also be seen as a vacuum instability in the sense that the Kerr solution is actually unstable against scalar perturbations in GR plus a massive scalar field. Okay. Now, the end point of this instability is the formation of a cloud around the black hole. So now I have changed color compared to the previous slide. The ergosphere is red, and the cloud is this blue region. The instability at some point saturates because the cloud extracts so much mass and energy from the black hole that at some point the spin falls down and it's no longer enough to sustain the stability. When the cloud saturates, it can be considered as quasi-stable, okay? And it's also long-lived astrophysically. So it's an interesting environment to look at. And yes?
The time scale of this instability?
Yeah, good question. It's extremely fast astrophysically. And the time scale is proportional to the mass of the central black hole, so it varies depending on what kind of black hole you're looking at. But just to have an idea, for stellar mass black holes, it can be hours. For supermassive black holes, say 10 to the 9 solar masses, it's 10 to the 9 times hours, which is, I think, 10 to the 5 years or something like that. So it's very, very fast.
Do you have to worry about this called backreacting on the metric?
Good question. Marginally. So an important question is, what's the mass of the cloud? There's a theoretical maximum, which is about 10%. The actual mass of the cloud can be anything from 0 and 10%, depending on the initial mass and spin of the black hole. So most of the back reaction can be 10%. If you look from far away, 10% of the gravity of the system is sourced by the cloud. So at your point, far away, 10% of the gravity is due to the cloud, so that's the back reaction.
I guess I was wondering if it could like alter the metric enough that the instability gets choked off, for example, and so you never grow to be that high. Because it seems pretty sensitive to the...
What feeds superradiance is the near horizon physics, where the cloud is never very dense. So if you look at the superradiant condition, it's a condition on the flux at the horizon, and that's, the black hole always dominates there.
What's the minimum spin that you need to start off with?
Okay, that's another good question. I need a chalk. Okay. So this is the mass of the black hole. This is the spin. So it can be at most 1 for extremal black holes. And for a given state of the cloud, so with a given value of the angular momentum, the instability region looks like this. Okay. So here I can also write alpha, where alpha is the gravitational coupling. So the product of the masses times g, which I've set to 1. Okay. Now the maximum value of alpha that triggers the instability for the main mode is 0.5. And the stability is above this line. So the minimum spin depends on the value of alpha. However, if alpha is very small, the instability is very slow. So this region close to the y-axis is not very interesting. Conversely, if you're here, then black hole must be extremely fast spinning to trigger instability. So there's a sweet spot here in between. If you want the formula for this line, then I can write it down. It should be I believe. You can check whether it actually agrees. I could get some factors wrong.
But so you need to be pretty close to 1, like the gap on the left side, like, I guess it depends on what's the lowest output you have, but you need to be pretty close to 1.
Well, for example, if you take alpha equals to 0.1, then this is approximately 4 alpha. So the spin must be at least 0.4. Yeah, if you increase alpha, then the speed must be higher. It's true. Okay. Okay, we call this system black hole plus cloud gravitational atom. That's for a good reason. It's because if you take the Klein-Gordon equation and you take a non-relativistic ansatz, so you trade the relativistic field variable phi with some non-relativistic wave function psi, and you expand in a non-relativistic series, then the equation you find exactly is the same as Schrödinger equation, this one, where the potential is like the Coulomb potential, except that the interaction is not the electromagnetic interaction between electron and proton, but the gravitational interaction, okay? Now, as I've already said, this alpha, we also call it the gravitational fine structure constant, must be of order 1 or a bit less, let's say 0.1, in order for the instability to be fast astrophysically. If it's too small or too large, then the cloud just doesn't go fast enough.
Why is the potential Coulomb potential but not U-cover potential? Because you have a non-zero mass problem?
No, this is just Newton's potential. So if you take the Kerr metric and you go far away, the first thing you feel is Newton potential. That's it. That's just it. Then, of course, there are relativistic corrections, which I have not written here. These ones are different from atomic physics because, you know, the fine and hyperfine structures are not due to the interactions between the magnetic moments and so on, but due to the frame dragging and so on. But Newton's and Coulomb's laws are the same.
By looking like close to the horizon or far from the horizon, based on that, the other terms might be important.
Correct. This is a non-relativistic expansion, so it's only true at large enough distances. However, because the radius of the cloud scales as the gravitational radius of the black hole, so GM divided by alpha squared. If alpha is about 0.1, then most of the cloud has support in regions where this is a good approximation. Okay. Now, same equations have same solutions. So we already know the spectrum and the eigenvalues of that equation. They are the same to leading order as the hydrogen atom. So we can label the eigen states and eigenvalues with 3 quantum numbers, quantum, even though this is a classical system. One is the principal quantum number, N, that tells you the energy of the state. L tells you the angular momentum. And then for a given N and L, you have a multiplet of states, which is broken into 2L plus 1 states by the azimuthal quantum number M. That tells you the angular momentum along the azimuthal axis. Okay, only some of these states can be superradiant, the ones with positive M, which I've drawn in red. So the fastest one, the one you may have in mind, just to have something concrete in your mind, is the 2-on-1 state. That corresponds to the 2p state in atomic physics. So the bipolar, the first excited states of the hydrogen atom. You can also have other superradiant states like the 3-2, that would be the 3D state, and so on.
Do you get the splitting in M because of the spin of the black hole, basically?
Exactly. So the analogy with atomic physics only works if you stop at Bohr energy. So alpha squared divided by 2L squared. The splitting between different L, that's the fine splitting, that's different from atomic physics. The splitting between different M, the hyperfine. In this case, it is indeed proportional to the spin of the black hole, because that breaks spherical symmetry, and indeed it's like the Zeeman effect, exactly. And okay, these are only the bound states. Now, just like in the hydrogen atom case, you have unbound states, the one with positive energy. Those are scattering states. Particles there just escape. Okay, are not gravitationally bound to the black hole. Okay, keep in mind this diagram because it will be useful for the things I'll say later. Okay, now people have tried to look for gravitational atoms in a variety of ways, such as by measuring the spins of black holes, because black holes cannot be too fast spinning if they develop a cloud. But today I'll be interested in probing these systems with a binary. So if you have a gravitational atom with a binary companion, then what happens? With particular emphasis on the gravitational wave signal. So for example, if you have a black hole binary, how is the dynamics of the binary changed due to the cloud? Can we infer the existence of the cloud from the modifications to the waveform? And it's quite like this kind of dynamics is very reminiscent of atomic physics. So you can use your intuition from quantum mechanics to understand what's going on with some caveats. For example, you find stuff like the analogy or the analogs of radio oscillations or the photoelectric effects and so on. And we'll go through a couple of these examples now.
Jimmy,
Yeah.
can I just step back for a second? In a hydrogen atom, it's the electron that has these states. Is it the whole cloud that's in these states and that's happening despite it being a macroscopic object?
So in the hydrogen atom case, the occupancy number is 1 or 2 if you take into account spin. In this case, what happens is that one particular state is unstable, so the occupancy number grows. Because it's a boson, there's no upper limit. So what you end up is technically a Bose-Einstein condensate, a very large number of particles in one quantum state, but because the number is so large, the system is actually classical. Because the occupancy number is what tells you whether the system is quantum or classical. It's a classical system, but the state it occupies is quantum in some sense. Okay.
Thank you.
The Bose-Einstein condensate is the most precise definition. Okay, so how do we do all these computations? Well, we just take the Schrödinger equation I've shown earlier, and in a non-relativistic approximation, we add a perturbation here. This is just the Newtonian interaction between the companion, or the binary, I should say, and the cloud. And this is a quasi-periodic perturbation because the binary orbits. It's not exactly periodic if you take into account the chirp, so the fact that the binary shrinks due to emission of gravitational waves. And for example, one central object in all the computations is the amplitude between two given states of the cloud of the gravitational perturbation. Okay, and we often expand this in a Fourier series. But yeah, that's the kind of computations we do. We use techniques borrowed from quantum mechanics. Okay, what's the first striking effect that one finds? Resonances. So when the orbital frequency matches the energy difference between two states of the cloud, then you can trigger a transition from one state to another. Like in this case, we are jumping from 2 on 1 to 3 1 minus 1. Now, the resonance condition can be imagined as particular orbits where when the binary hits that orbit, then the cloud starts the transition because the frequency of the orbit matches the energy difference, okay? And we can link we can find what's the resonant frequency, for example, for intermediate mass black holes, which admittedly we don't know if they exist, but that's just an example. The frequency of Bohr resonances, so transitions between states with different n, falls in the Lisa band, so millihertz. Okay, now qualitatively, and I'll go into deeper detail later, what's the impact of resonances on the waveform? Well, if you transition to a state that is higher in energy, then the binary is in fact giving energy to the cloud because it has to jump higher. So this energy is taken from the binary. So that means that at resonance, the binary is losing more energy than what you would expect from gravitational waves only. Okay, and so you have the so-called sinking orbits. So periods of slightly accelerated spiral. Conversely, if you jump to a state with lower energy, then the binary is absorbing energy from the cloud, so it can replenish its energy. Okay, and you have floating orbits, periods where the orbital frequency evolves much more slowly than you would expect from vacuum spirals. Okay, I'll go into deeper detail on resonances later.
So how much more slowly? Could you park it until?
Yeah, you actually, in most cases, you reach an equilibrium. So the derivative is in fact 0 for a long time until the transition is complete, and then the spiral resumes. So in fact, you have a truly floating orbit. So a monochromatic signal for a long time, then the cloud is just completely transitioned to the other state, is no longer able to sustain the resonance, and the binary moves on. Okay, the other main effect to have to know is the analog of the photoelectric effect. Okay, now famously, if you shine a laser on a piece of metal, nothing happens if the frequency is not high enough. But if the frequency is high enough, then it's able to give enough energy to the electrons to jump to the continuum states, and they do photoelectric effect. And in this case too, if the frequency of the binary is high enough, then the cloud can jump from its bound state to one of the unbound states and escape from the system. We call this ionization, or in analogy with atomic physics. And once again, you can imagine this threshold frequency as a threshold separation. So when the binary is more compact than some given separation, this effect starts. Okay, now to be precise, this is not quite like a laser, because a laser is a monochromatic perturbation. In this case, the Newtonian perturbation is not monochromatic. It is periodic, but it has multiple harmonics in it. So it's like shining multiple lasers with all the harmonics, okay? So there are multiple threshold frequencies. But okay, the physical intuition is the same. How do we compute the rate of this process or the power lost in this process? The simplest possible way is just with Fermi's golden rule. So the rate of the process is just proportional to the matrix element of the potential between the bound state and the unbound state. And you have the constraint on energy conservation. So the final energy is the initial energy plus an integer multiple of the orbital frequency. Okay, we can find the total energy lost in this process by just summing up over all final states. You get some complicated formula. So rather than going through the formula, I'll just show you a plot where I plot this p ion, the ionization power, normalized to the power loss in gravitational waves. Okay, so before looking at the plot, just for comparison, in the top panel, I've plotted the profile of the cloud for some parameters. So for these parameters, the cloud peaks at 50 gravitational radii, okay, in the same order of magnitude I've written there. Okay, now let's look at the bottom panel. There are two main things to notice. First of all, this plot is discontinuous. What are these jumps? What's going on? Well, those are exactly the threshold frequencies I was mentioning earlier. Once again, as I said earlier, you don't have just one, you have multiple of them. Then you may ask, okay, but why is the jump finite and not 0? Well, that's a question that requires a longer answer. So you may ask this question later. For now, just believe me, the jump is not 0. And these are actual discontinuities, unless you take into account the fact that the frequency slightly evolves with time. And so that actually smoothens out these discontinuities a little bit. In fact, power loss, of course, is not a discontinuous function in reality, but for all practical purposes, those are actually quite vertical jump, okay? The second thing to notice is the scale of the y-axis. Okay, now I'm not taking particularly optimistic parameters. For example, here I'm fixing the mass of the cloud to 1% of the mass of the black hole. That's conservative, can be up to 10%. Okay. Still, ionization is a huge effect. It can be orders of magnitude larger than gravitational waves. in a given window of separation. So if you go too close to the black hole, then gravitational waves become just too strong. If you're too far away, then you're not inside the cloud, so this effect is not important. But in a large range of separations, ionization is not just a perturbation to the binary dynamics. It's the main effect that drives its evolution. Okay, what's the signature of ionization on the gravitational wave emitted? Okay, let's look at the evolution of the frequency over time. I've rescaled it in a bizarre way, in such a way that the vacuum evolution looks like a straight line. Okay, so the black line would be the vacuum evolution, and I'm here only using the quadrupole formula. So at late times here, post-Newtonian effects enter and change the frequency evolution. But okay, when you take into account ionization, the inspiral is much faster. So the frequency goes up, so down in this plot because this power is negative, much faster. But what's most striking is that there are these kinks in the frequency. Okay, those kinks correspond to discontinuities of the previous plot. That's because a discontinuity in the power lost is a discontinuity in the first derivative of the frequency. And so it's a kink in the frequency evolution.
So if you extend this in this direction, the curves go down back to the black.
In this direction?
The earlier.
This direction, at some point they become parallel to the black line, but they don't converge to the black line because you still have a difference in the merger time. So the system will always be.
You're not losing any different energy, but okay, because you normalize T minus T naught, then you're shifting.
Exactly, exactly. Otherwise, they would converge, but then one system merges earlier and another system merges later, but I've shifted them in this plot, yeah. To be fair, this plot also takes into account other effects like accretion on the secondary object, but the main thing here is ionization, yeah.
So you've got co-rotating and counter-rotating. But there should be spin of the second black hole and then also an orbital spin.
Okay, co-rotating and counter-rotating refer to the fact that the cloud itself has angular momentum. So the orbit here, it's assumed to be planar. We also have the same thing for inclined orbits, but for simplicity, let's assume planar orbits. They can be either in the same direction or not. The spin of the secondary object enters at higher post-Newtonian order. So it's not visible in this plot.
Well, why this huge difference between counter-rotating and co-rotating?
This is actually a bit hard to explain. But roughly speaking, the physical interpretation of ionization, perhaps surprisingly, is that its back reaction on the orbit is dynamical friction. Okay, so dynamical friction is the same thing as ionization. This is perhaps surprising. But so dynamical friction does depend on the relative velocity of the object and the medium. Okay, so if you spin in the same direction or the opposite direction, this changes, and so you do expect some difference.
Right.
Just to give some physical intuition. Why is it exactly like this that counter-rotating looks much stronger? Then I should say, yeah, it does look much stronger in this plot, but this is normalized with a function that depends a lot on, like, as the fifth power of the orbital separation. So if you remove that, the curves actually peak around here and they look quite similar. So there's no super big difference. It's just that this difference at large radii is exacerbated by normalizing to the power loss in gravitational waves. Okay, just to conclude this part, in this case too, we can predict very well the position of the kinks. Okay, so if we see kinks in the frequency and maybe more than one, we know exactly how to link them to, say, the mass of the boson, the state of the cloud, and the order of the kink. So this is just an integer number that counts. Okay.
Why are you always picking to normalize the one mass of the black hole that we don't know that it exists? Right?
Well, fair enough. I mean, honestly, I mean, you can play with parameters. If you take 10 to the 9, this is just too low frequency to be interesting for a detector. If you take a solar mass black hole, then you can make this interesting for even existing detectors. The problem is during the spiral, ionization actually evaporates the cloud, right? And this is a much more important effect if you have an equal mass system.
Unequal or equal?
Equal. So if the companion is heavy, then it destroys the cloud more efficiently. So if you're interested in, say, LIGO Virgo, then frequencies are a bit borderline, but most importantly, ionization destroys the cloud too early. So it's hard to justify.
Before you get into the LIGO band.
Exactly. As soon as yeah, very, very early.
Remind me, maybe I should know this, but even for the neutron star type of mass, how far we are in gravitational radio when it enters in the LIGO band? In this block. I mean, that's the place where they are the first.
For neutron stars,
I mean, solar mass type black hole. Say, two solar mass.
For neutron star, I'm not sure because the GW17 and 17 we've seen 3,000 cycles, which I'm not sure what corresponds in separations.
Probably it's still not very far.
For black hole binaries, it's just a few gravitational radii, which is not enough. But let's come back to this question later, because one of the things I'll say at the end, I think makes equal mass binaries more interesting.
So what sort of mass ratios do you want?
Yeah, good question. So we are assuming small mass ratio to do this computation. It's not super easy to quantify. We have quantified it depends a bit on the parameters. Smaller than 10 to the -2 should be fine. Okay, but I think that's a conservative estimate. That's my opinion. That's an estimate we had done in appendix just to quantify it. But I think at most you will have another one change in the plot. Okay, it doesn't completely change the. Okay, let's move on to the second and final part of the talk. Okay, we know there are these two effects, resonances and ionization. Both of them have striking signatures on gravitational waves. They can be observable provided they are in band and the cloud is there when the separation is small enough. So about where the cloud is, so 100 gravitational radii. There is one problem. And that is you also have fine and hyperfine resonances. Okay, so those are between states with much smaller energy splitting. So the frequency is smaller, so it means they happen much earlier during each spiral. So to understand what we actually see, you should understand the history of the system. So how, for example, how is the state of the cloud changed by the earlier frequencies? So what's the actual state we expect to find eventually in band? Does the cloud survive all these earlier frequencies? As I'll explain in a moment, that's not always the case. And in general, what is the configuration of the binary we expect? So in general, we have to study the history of the system to understand what we actually find in like with both resonances and ionization. Okay. So diagrammatically, this is where we may observe the system. And I want to replace this question mark with some more insightful diagrams, okay? Okay, this is like answering this question, the history system is quite intricate, and I don't have the time to explain all details, but I'll just give the upshot, so the main conclusions, okay? The first thing to have in mind is that these fine and hyperfine resonances, the first one that happened in history, are all floating and decaying. So floating means that you jump to a lower energy state, so the frequency stalls for a long time. Decaying means that the final state is not superradiant. So if you transition to that state, it's just reabsorbed back into the black hole, okay? And effectively, this destroys the cloud. So each of these two things has its own characteristic timescale. So for how long the frequency floats, and how long does it take for the state to be reabsorbed by the black hole? So it's mandatory to compare these two timescales to understand who wins. And the answer is, in all cases, the flow timescale wins. So basically, if you ever trigger any of these fine and hyperfine resonances, you just destroy the cloud. Okay? Because as soon as you transition, well before the float completes, the cloud is gone. It's just reabsorbed. So we can already partially answer one of the previous questions.
But it's such that then the spin of the black hole
Would
falls
change.
outside, and you will not generate a cloud again.
Correct. That's because, so if you jump, so this is a positive angular momentum state. So if you jump to this negative angular momentum state, the black hole is absorbing negative angular momentum. So if it starts here, grows a cloud, stops here, and then has this kind of process, then it falls back here. So it's not in this instability region. So it cannot grow a cloud again. In general, the only thing that can make black holes grow clouds again is if you give them angular momentum from outside, like with accretion. Okay, that can actually make the cloud grow again. But in isolation, once it's grown, that's it. Okay, so these fine and hyperfine resonances are never able to change the state of the cloud. They can either destroy it if they are ever triggered, or somehow the cloud can survive if we do not encounter these resonances in the evolution. Okay, so in general, we only have two possibilities. Either we go through, we're safe, and then we have these interesting observational signatures, or the cloud dies here, and then we only have a vacuum binary after that. Okay, so now we want to understand under what conditions we fall into one of these possibilities. Okay, to understand that, this is a very technical part, which I don't have the time to explain. I'll just tell you the main ideas. We have to understand resonances much better in the sense that the usual picture that one says when talking about resonances is that they're like the so-called Landau-Zener transitions in quantum mechanics, which is something that Landau-Zener found in the 30s, something apparently is well known in quantum mechanics. But so you take a two-state Hamiltonian, those are the energies of the two states, some perturbation. With some unitary transformation, this can be put in this form, where tau is the time. So you have energies with states with energies that change linearly with time. And so this is the Landau-Zener Hamiltonian that indeed reproduces a transition between the two states. And you can link how much the cloud does this transition to this off-diagonal element, which is called the Landau-Zener parameter. Now, so it looks like this would be the case where the resonance is not triggered enough. This would be the case where the cloud is completely destroyed. It's actually a bit more complicated than that, because this linear time evolution does not take into account the back reaction. So the actual equations should take into account the fact that the energy and angular momentum of the cloud backreact, basically. So it's more complicated. Instead of that Hamiltonian, you have something like this, where omega has now its own equation, and it's not just time, but it's something that depends on the occupancy number of the cloud itself. And this makes the system much more complicated because it's now nonlinear. Okay, it's no longer a Schrödinger equation with some funny time dependence. It's actually a nonlinear equation. So it's very hard to solve. You cannot solve it analytically. But still, there is a lot of insight to be gained analytically, somehow, which I don't have the time to explain right now. So I'll just say the conclusions.
What does that depend upon? Landau parameter.
Yeah, the Landau parameter depends on the strength of the coupling between the two states and how far you go through the transition. So if you go very far, so if the spiral is very fast, then you don't transition much the cloud. Instead, if it's very slow, you have an adiabatic transition, and you fall in this case here. So most of the cloud does the transition. That parameter stays the same in the nonlinear case, but it's the frequency that changes in a non-linear way. That makes things much more complicated. But okay, so a lot of technical works goes into understanding this coupled nonlinear system, even though it looks very simple. So what's the answer? The answer is that you have very weak resonances. So in fact, you don't trigger these early fine and hyperfine resonances if the binary in the cloud rotate approximately in a counter-rotating way. So that's what I was explaining earlier to Eric. Within some tolerance. So we have computed the angular interval within which these resonances are not triggered. Otherwise, resonances are very strong, and as I said earlier, they destroy the cloud. Okay, so the orbital inclination is the main parameter that distinguishes between the two cases. Okay, so now I can go back to the previous plot and add the y-axis. That's the orbital inclination. So we can say, okay, the case where the cloud dies, it's when it's not close enough to counter-rotating. The other case, it's within some interval, some angular interval that depends on a certain way on the parameters. In that case, it goes through. So the main conclusion, the main obvious conclusion is that if we observe resonances and ionization, we expect the state of the cloud to be the same as the original state. It doesn't change due to early resonance. And second, the binary is expected to be almost counter-rotating because all other binaries just don't go through the early phase. Okay, and we thought, okay, that's the end. That's what we can actually observe. But then there's actually a small surprise, which I think is quite important. This actually partially answers your question. These are all direct signatures of the cloud. So if the cloud is there, it changes the dynamics, and we see this live in the gravitational waves. But the destruction of the cloud itself changes the parameters of the binary. So even though the cloud is destroyed, it leaves a mark, a permanent mark on the binary, which is then carried by the binary through its evolution. So what's this mark? The evolution of the eccentricity and the orbital inclination. So during resonances, the eccentricity and inclination evolve in a very peculiar way. And I've already said this in one of the Astro Coffees. There are many interesting features here, but one important one is that you have fixed points of the eccentricity. So they can be either 0, this is 0.46, and there are a few others depending on what exactly is the resonance that you're exciting. And so while the cloud is being destroyed, the binary evolves towards these fixed points. Okay. And when then the cloud is gone, you're left with, for example, an eccentric binary, or a binary that is quasi-circular and has but it's equatorial. Okay.
But the eccentricity then decays by the gravity.
Correct, indeed. Then gravitational waves wash away the eccentricity. However, this still remains more eccentric than binaries that didn't have this kind of thing. So yeah, both like eccentricities decay, but they never cross each other. So you still expect, but in band binaries more eccentric than otherwise. In fact, there is a paper by Rafael Porto and two collaborators that found some of the results independently from us. And they answer more the question of what do you actually expect to find in the LISA band? And they found indeed that there's a higher number of slightly eccentric binaries.
Why
Okay.
are there so many fixed points? Do they correspond to different transition?
There are only two, one here or one here.
No, here you would write 0.46, 0.58.
Oh, sorry, yes. Exactly. They depend on the angular momentum to energy ratio exchange in the resonance. So each resonance has its own fixed point. Okay. Now, the obvious question is, okay, how close to the fixed point you get? And this depends on a parameter, which is this d, like the distance parameter, how much distance you travel. For example, that's larger for more unequal mass binaries. Q is the mass ratio. But in general, roughly speaking, so for different shades of color, those are different values of d. The larger d, the closer you get to the fixed point. And for reasonable parameters, again, more unequal binaries get closer to the fixed point. You get quite close to it. You have fairly equatorial binaries, and you can get quite close to the 0.46 or 0. And so the way to look for this kind of signature is compare the eccentricities and inclinations of a population of binaries detected through gravitational waves to what we expect from astrophysics, okay, from some combination of formation channels. It's complicated, yes, I know. But yes, that would be the signature when you don't, this is the indirect signature. Okay, and yes, that's it. I leave the conclusions here. Thank you.
If you have like vector bosons
Yeah.
powering superradiance in the cloud, do you expect significant differences?
So superradiance can happen with vector bosons. In some sense, it's even more interesting because these so in the scalar case, the first superradiant state is has non-zero angular momentum. Okay. With vectors, because the field itself has angular momentum, you can have something with zero orbital angular momentum, but with the spin intrinsic angular momentum, it can be superradiant. And that's much denser, closer to the black hole, so it grows faster. And you could also probe shorter distances. You can go closer to the black hole.
The dark photons can be.
Exactly, dark photons. Now, there are two issues, in my opinion. First, the theoretical motivation, as far as I know, is a bit weaker for dark vectors than for dark scalars. And second, it's not a problem, but it's just that no one seems to have studied the case with a binary in the vector case. So, yes. Well, there are a few studies, but they don't study these effects. They study simpler effects like the quadruple field or something. Yes, just I
guess you kind of commented about this throughout the talk, but I guess there are like all of these bounds that you need to respect to have some kind of interesting thing happening. Like you need some range in alphas so that the cloud, I don't know, grows fast enough, doesn't decay fast enough. Some range of like mass ratios, the cloud can't be destroyed. So am I incorrect in thinking that the range of like parameter space where this actually, where there's anything interesting actually happening is quite small? Or
So it is true that with alpha, so with a given black hole,
And like the
You can-
spins, like for, I guess, given the range of not just the say like the mass of the scalar field and whatnot, but like the binaries that you actually need to exist, right? You need some.
With the- I'm not so worried of-
ratios.
okay, so let's go through all these things. With alpha, it is true that with a given black hole, you can only probe, let's say, less than 1 order of magnitude in alpha. Let's say from 0.1 to 0.4, okay? But that just means that if you look at a stellar mass black holes, you constrain one given mass window. If you look at supermassive black holes, you constrain another window. Now, for the spin, the black hole needs to start with a fast spin. There's a small caveat to this in the sense that other states, so this would be the instability region of 2 on 1, okay? But then there are other states, and they look like this. So this extends both the range in alpha and in spin. So especially for light black holes like solar mass, the constraint on the spin is actually not strong. We can look at the plots later. So for the binary, the mass ratio, so our computations are done with small mass ratio because it's useful to have a perturbative bookkeeping parameter that is small, right? But most of the results, for example, the resonances don't assume that. And so the indirect signatures on eccentricity and inclination don't depend on that because you don't have the clouds, you're not worried about destroying it. The resonant, like this kind of thing happens even if you have an equal mass binary with a large separation. And so these kind of signatures can, like, is interesting for equal mass binaries as well.
That relies a lot on this like astrophysical distribution.
Exactly, that's the very hard part. You need to control very well astrophysical uncertainty to be able to do this kind of statistical analysis. Yes, and then that's what Matthias said. You need to play. It's a bit hard to play with the mass of the black hole and the detector frequency if you want direct signatures like ionization. Now, in my opinion, if they exist, intermediate mass black holes would be perfect. But the question is, there is one confirmed intermediate mass black hole in, I think, the Omega Centauri cluster, and confirmed. And
more confirmed that they both.
But yeah, that's the problem. So I think, yeah, there are quite some constraints, but it's not super hard.
Let's have one more question and then we'll carry on at lunch.
Yeah.
What you showed on one of the first slides, how this cloud would look like, for me is to recall this backreact disk, accretion disk, the standard like.
Yeah, sorry, I didn't fully understand the question. Are you referring to what I discussed during the Astrophysics?
Just showed for how the superradiant instability lead to the formation of the disk. On one of the very first slides.
Oh, the Penrose process?
So for me, this.
When there is the cloud.
Yeah,
This.
this one. This one for me recalls what like people study a lot of the standard accretion problems. So like this is the initial shape of the disk. And do you expect, if my analogy is correct, do you expect that we can observe something like the MRI instability in this sort of the disk? Because it's interesting to see what happens when.
So I should say this is much more compact than accretion disks. I'm not an expert on accretion disks.
Yeah, but I think this is pretty similar because that solution was derived in a sense that the specific angular momentum is constant. So this is pretty much short.
Oh, I see. I see.
Quantum state.
For the instability, I'm not sure.
Okay, on that uncertain note, let us finish. Let's thank Jimmy again.